Hello, everybody. I'm just going to give you a few minutes to get in. Hope you're having as lovely, beautiful days we are here in Lincolnshire today. It's been a lovely blue sky, a little bit chilly, but you can pretend when you look out the window. Super. Some people coming in now. Okay, well, I'll just take a couple of mo's to introduce what's happening today. So welcome to our latest Inform webinar. My name's Joanna and I'll be hosting in the background, very much in the background today. The Inform webinar series have been designed to give you the opportunity to learn about the latest advances in technology from those working in research and manufacturing. And we're pleased to be able to showcase the latest collaboration from Tinius Olsen this afternoon. Just like to give you a bit of housekeeping for the question and answer bit. Once the chaps have finished their presentation, always really keen to answer any questions that you may have. Please, can you use the Q&A box at the bottom there to pop your questions in, not the chat box, because sometimes if people get chatty on there, it disappears and we don't want to miss any really good questions. Okay, so for the Q&A box would be wonderful, and Sean and Matthew will address that at the end of their main presentation. So thank you very much indeed. I'm really looking forward to this. Really now over to Matthew and Sean, who are going to talk to you today about the future of exoskeletons. So please, guys, over to you.
Well, good afternoon, everybody. Thank you for giving us the opportunity to speak at the IOM3 event. My name's Dr. Matthew Dickinson, and I work at the University of Central Lancashire. Sean?
Yes, good afternoon and good morning and maybe good evening, depending on where you're located. My name is Sean Bird. I am the technical director for a multinational company, Tinius Olsen. Matthew and I, Dr. Dickinson and I, have worked for a number of years integrating the technology that he's using along with the platform of Tinius Olsen as a leader in testing, coupled along with different international standards and how they apply and how they're compliant with the testing to move forward a exciting project such as this. So thank you for being here. Matthew?
Thank you, Sean. Yes, so today what we're going to do is going to discuss the future of exoskeletons. What I wanted to do is to give you an insight. Now, I'd like to just spell out way before we begin of what I've done is highlighted some major advancements over the time periods that have occurred. So if I was to put every single advancement in exoskeleton technologies in this presentation, it would be a very long and very messy piece of work because there is an awful lot of great things that have happened. But first, let me just say thank you to Tinius Olsen and also the university that I work at. We do a lot of collaborative approaches. We've invested an awful lot of money in our student experience and a lot of development throughout the university. So it's quite an exciting time to be part of engineering and quite an exciting time to forge new collaborative behaviors and new collaborative partnerships with businesses. Anyway, this aside, now somebody once said to me that the best things to be able to consider the future of something is to know where it once was. So what I thought I would do is first really discuss the exoskeleton in its highlights. Now, again, I'm sure those of you who are already aware of this technology will know that there's an awful lot more that's occurred within this area, but I've tried to capture some of the biggest steps. The first one, which always makes me smile, is that the idea of that the original exoskeleton, the very first, was actually in 1865. And well, 1865 to just into the 1900, completed by Nicholas Yargan. Now, Yargan, his original idea, what this brilliant Russian inventor was considering, he was considering springs. He was considering the idea of a leaf spring. And this idea, I laugh now, but wait till I show you the next piece. The idea was that he was attempting to attach this spring to the back of his leg to actually try and passively have some of the loading from each step into these springs to, in essence, assist his motion. And when you first look at that, you think, yeah, that's crazy. If he'd have attached something like that to his leg, it would have been detrimental to his health instantly. Well, we already have these out there. These already do genuinely exist. For those of you who don't know what these are called, these are known as power striders. And there are a lot of youngsters, I wish I was that fit, but a lot of youngsters use these to be able to do some incredible stunts, jumping and really showing that. Now, this is based purely off this exact same theory that Nikolai Yarkin was proposing. Interestingly, he never actually completed this piece of work. He owns the patents there, but he never completed the piece of work. So in reflection, he wasn't too crazy in his suggestions. He was just very much ahead of his time. Now, when we consider from the early stages, we move into Leslie Kelly's developments, where what he was doing was building on Nikolai Yarkin's suggestions, and actually said, perhaps we don't need to be around the hip area. We should be looking at the upper back area and actually supporting it that side. His developments did start to influence how we look at exoskeletons to this day. Some of his suggestions weren't the best, but they were key things. It wasn't until 1960 where GE commissioned for the Hardyman to be developed. Now, the Hardyman, revolutionary of its time. I mean, we're talking 1960 of this being actually built. The idea was to do away with the need for forklift trucks, allowing every employee to have the strength, the ability, the mobility to be able to move around and be able to support lifting and moving large structures like this around. Problem with this design, it would run for 5 minutes and then start to run short. However, we cannot take away that it was a failure. It's more of a success because of what he was doing and the process with it. It's fascinating what had really occurred here. When you actually move further down the line, we start to hit the noughties. What we really start to see is some key developments. Now, one key thing I quite like on here is one called the life suit. This was completed by Monty Reed, who was an US Army Ranger who broke his back in a parachute injury, and he was determined to walk again. So he built a hydraulic system that allowed him to move. Huge advancement to say it was 1986 when this happened. But when we hit this larger area into the noughties, we start to see massive things occurring. Now, at this particular time, technology becomes cheaper, microcontrollers become cheaper, the motor itself is refined. Some of the biggest advancements by MIT really allowed people to start looking at how motors could be applied actually in the exoskeleton system and even into other technologies as well, not just the exoskeleton. At this same time, DARPA then start to say, well, if we've got a skeletal structure, could we not be trying to mimic the muscular behavior? And then the exosuit is born. This is a soft approach which mimics that contraction, that movement, and that element. This then moves on to further things. So we start to see the Hulk being defined. And interestingly, not until 2016 was the exoskeleton actually defined. It was never clearly defined, and it was never noted about what that exoskeleton would, how it would actually be seen until ASTM, well, a group of 6 sat down and said, right, this is what it needs to be. And they defined it as a wearable device that augments, enables, assists, or enhances posture or physical activity. This is groundbreaking, because what it then does is it gives us an operational platform of how we can be starting to perceive these things. ASTM itself really started to notice that this technology was booming. Massive elements were going on. This led to the ASTM F48 being born. This would occur a year later in 2017. Now, you may be a design person, you may be a person who's considering the human element side, or somebody who's considering the environment and how these systems should be used. or you may be somebody who's thinking about risk management and also about how we actually refer to these things. The point of this slide and the point of what I'm trying to spell out here is this is not completed by just one particular field. You could not complete this as just being a mechanical engineer, for example. This is a collaboration across an entire area of genres of skill sets. And this is why if we move towards the development of exoskeletons, when we progress this technology, we need to, it's fun, don't get me wrong. It is incredibly fun, but we need to consider these processes carefully and as safely as humanly possible. And that's where the international standards, the ASTM international standards really comes into play. Because what you'll end up with is a collection of industries and also academia, people within the research and the manufacturing side, discussing their best do's and don'ts of the processes. If you are ever interested about searching this out, I do have a link at the end, and please do reach out because I'm sure the F48 will be happy to hear from you.
Hey, Matthew, do you mind if I just jump in here real quick?
Absolutely.
So, as I'm looking at this slide initially, and I'm looking at all the things that are here, I think it's important to note to our audience that there is no collective view on trying to commercialize what we're trying to do here. What we're trying to do is make society better. We're trying to put the technology that is multinational. It doesn't matter if you're in Australia or if you're in Lancashire or if you're in the United States or in Canada or Mexico. What we do is we go into these meetings knowing that our information may have been simultaneously developed in another part of the world. And this is more like a think tank, if you will, where we want to be collaborative, safe, and expectant of technology. What that means to us is that we don't always have the best ideas as a single entity, but collectively we can put this idea to work. We can utilize all the different people that are available to this technology and move it forward in a more expeditious manner. And that is how Matthew and I got connected a number of years ago. And I'm just going to take this opportunity that Matthew went from being a renowned professor at University of Central Lancashire to being a subcommittee chairman on this particular committee. And to say that he got his eyes opened would be, I think, an understatement, but I don't want to speak for Dr. Dickinson. But I will say this, that as the world of testing and development of cutting edge technology is involved, please keep in mind that all these things have to be tested. And it doesn't matter what it is, everything down to the smallest microchip, all the way up to the largest exoskeleton or exosuit. So with that in mind, we formed a partnership, Tinius Olsen did, with with the thought of seeing something so amazing come to fruition and not just sit on a white paper inside a university. We want to see this because it's amazing, and the technology that the folks at MIT and NASA and at various universities, this is how we get it into the society. And believe it or not, and I'm not going to steal Dr. Dickinson's fire here, but most of this came to about because of a young 15-year-old previous student of Dr. Dickinson. And that kind of gave him the creative push, as I would call it. And I gave Matthew, I would say, the technological push for standards compliance. And with that, the collaboration between Tinius Olsen and this university, UCLan, and Dr. Dickinson and the team at Tinius Olsen has come to fruition. So I just wanted to point that out to everybody if you're out there wondering how we came to be together. Thanks, Matt. I appreciate it.
Yeah, no, that's no, thank you. Thank you. What I do want to do is just give you a bit of a highlight, because in this slide in itself, there's a lot of information here. And what I really wanted to do is just really give you food thought, a little bit of food for thought in essence. So when we consider design and when these things were defined out, we have the passive structure. Now, someone once said to me, how would you define a passive structure? How would you define how the passive behavior works? Now, I do appreciate some of you who are listening may know exactly what I'm referring to. But if you think of a crutch, you lean onto a crutch and you're in essence trying to relay some of that force from that crutch down into the ground. And by using complex mechanical structures and mechanisms, we can make a structure which will go around your body. And that is what we would class as a passive exoskeleton system. If we consider the quasi-active exoskeleton, what this refers to is spring linkages. So if you think of a spring, and if you think of loading the spring in equilibrium, if you consider to the bottom right, for example, this is Ottobock's exoskeleton, which is considered to help the upper body to relieve strain. What this uses is a balancing method. For those of you who can really visualize this, a steady cam is a great example. The large structures that a lot of cameramen will wear around the chest to hold large cameras in place. These are miniature steady cams, which are in essence mounted to the back, and they help the arm and relieve the arm whilst it's upright in a state. Again, all the purely mechanical and spring-based actuation. So from the left, this is mobility exoskeleton, looking at supporting around the lumbar and also supporting around the quadriceps, helping somebody maintain that stance, right through to the military, from the Mawashi uprise exoskeleton, which again uses the exact same principles, right to, as I just said, the Ottobock. However, you may be considering active. Now, this is the two elements on here which I really was excited to discuss with you all. To the left is what a lot of people consider to be the active exoskeleton. It's a large structure around the body with big motors on it that allow the body to move around. To the right, this is an exosuit, which has been developed by Harvard. Harvard in themselves have been looking at the idea of assisting muscular motion by cables and fabric and using the Bowden method, which is in essence a cable which will slide in between a housing or a shielding to minimize the coefficient of friction. It's an incredibly good idea, really good. And some of their demonstration pieces that are shown to date are very impressive, extremely impressive, in fact. So when we're considering design, some of the things that you really need to think about is how to support the body, holding the body, where to actually attach fixtures, and how we do it. Some of colleagues who I've worked with on the F-48, some of their approaches are absolutely ingenious, and you'll see them across the entire world, some of their actual applications for it. But when we're considering design, it's about trying to come up with the best way for it and how to support around the body. Now, I love this one. And this, I've thrown these large structured exoskeletons on there because that is the first thing that you'll all think of when you think of exoskeleton. You'll think of a large structure that's around the body and you'll think, oh yeah, that's what it's for. When really human factors and the environmental application of what we're doing mean that you could have an exoskeleton which is designed to help you if you're working in a steel factory, where granted, this will be a large structure. But if we're considering the usage and safely doing this usage, if you're somebody who's working in, let's say, for Amazon or a postal service, this is the type of exoskeleton that you would be seeing a lot more of. Now, commercially to the left is the Noom exoskeleton. This is, as they nickname, the chairless chair. The idea of this is in the UK in particular, around 30% of factory injuries come from trip hazards. One of the major trip hazards on the factory floor is stools being left in place. And if you're on a factory floor where there's extremely expensive machinery and dangerous machinery, they're looking to remove the stools off completely to remove some of that factors. The one to the center and to the right, they're both from a German company, and then considering about the lumbar support. If you're bending over, Now, I don't know what you guys are like, but when I was a child, my mother would always say to me, lift with your legs, lift with your legs. And regardless of how many times you tell yourself this, you never do. Everybody ends up lifting with the back, and everybody says, oh, I've hurt my back. Now, jokes aside, this in a workplace condition can lead to a lot of further injuries and a lot of rehabilitation needed. This has a big impact on our health services. And what companies are aiming to do is to try and support the lower areas, to support the lumbar areas, to, in essence, stop you from trying to lift with your back and almost guide you and assist you in doing it right. This is where, when we roll it back and think about standards, if we're trying to map this procedure and if we can help guide the design, we can then look to the future of making this type of technology not super expensive, but a lot more affordable for every person to get this type of technology. And this is where I'm going to lead to, by the way. And this is an interesting one for me. So when we consider disposal, if you think of throwing things in the bin, we can't just simply make all this technology and say, right, okay, let's just throw it away. We need to really consider about the green impact of this. If we're going to design something for rehabilitation, right through to supporting the manual worker, how we dispose and how we design and how we maintain our equipment is vital. We need to ensure that the materials that we use are the right type of materials, and the testing that goes on is where companies such as Tinius Olsen, the machines that we would use are to consider the material after testing. And once it's ready to be, if you will, if it's ready to be disposed, what materials can be kept? What materials are recyclable? Because if we can recycle some of the materials that we use, we're in a position where we're creating hardly any waste from what we get. And that's great. But there's one other element about exoskeletons, which I've not really even discussed. Almost every skeleton you've seen has a sensor on board. It records data. It may record position of your spine, your arms, your legs. It may record personal data about you. So when we consider the disposal of this equipment, it's not just the physical that we need to consider. It's also data that we need to consider. Because if we get to a position where the technology that we're generating isn't properly secure and properly disposed of when completed, you can end up with a lot of personal data just simply on a rubbish pile, which is not the aim, and hence why we need to consider that. Go on, John. Oh, you're on mute. You're on mute.
Thank you. So when I'm listening to you say this, I think it bears in mind to let our audience know that we've moved from what was happening in the 1800s, which was based on ferrous materials, iron, etc., all the way to today to additive material, which is printed 3D material, and in everything that's in between. And the beauty of not only printed material that might be a composite style material, or printed additive material, which could be something as light and strong as a titanium. All these things can be recycled. And yes, we're talking about the data, but what we want to impress upon our audience is that as I look at this, if you were to think that this was made out of just a plastic or a polymer or a polypropylene, you would be mistaken. A lot of these materials are made out of additive material that may be hybrid materials. And we need to keep that in mind and how it interacts with our human body, which I know that you and I have talked about in the past. But along with the disposal of it is, how do we test it? And because this is such cutting edge technology, we're on literally the precipice about how to do it right. And we're still learning as we go. And that's the exciting part about having multinational individuals sitting in these rooms trying to figure out, are we testing it right? Or are they testing it right down in Australia? And I just wanted to take this opportunity to say, when I see this, I'm just amazed about how the technology has moved us forward, along with the testing of this particular technology.
Yeah, exactly. And it is exactly that. You're absolutely right. Your old ferrous materials are completely obsolete in this particular element. But when we consider this now, we can consider composite. We can consider so many different things. It's quite an exciting time to be alive. And this really starts to really prompt the discussion that little bit further. And this is where I wanted to move on to the future. I want to really just discuss about where we are at present. And again, I know there is so much in this that I've probably not really highlighted to a large degree, because I really wanted to open up a lot further about the materials and a little bit where it's going. So where could it be going? Now, just yesterday, MIT, if anybody's ever heard of the famous Professor David Newman, if you haven't, do get online, have a look at some of the stuff that she's been doing. Phenomenal. I'd love to just say engineer, but she's really not. She's kind of like a mix of everything. But what they've now proposed is not proposed, they've actually produced, I should say. They produced a prototype of a new flight suit. Now, this is what they've been nicknaming the 3D knitting. So if you think of the old weaving machines that came out of the 1800s, what they've actually done is they've looked at producing a material which weaves a specialized material under particular fabrics with particular electrical charge through it. You can control feedback, you can get live feedback, pressure feedback. This is, if you will, a great way to describe this would be the shoes from Back to the Future 2 that Marty McFly puts on, where the shoe actually closes around his leg. This is a genuine application of this. And I'm actually quite privileged to know some of her research team, again, through the collaboration that I've been doing with Tinius Olsen and through my links with ASTM. So I'm quite privileged to have met some of her team already. And but this really prompts further points. The materials. Colleagues that I've worked with are presently looking at the idea of non-Newtonian. So think of it as a foam. If we're considering foam, now foams, non-Newtonian foams are fascinating. The idea of that under zero loading, they will not stiffen, but under larger loading, they will stiffen. The big question is, could we be moving towards a future, which I firmly believe we could be? We be moving to a future where our non-Newtonian foams will stiffen when needed? Our exoskeleton will be our work clothes, our safety clothes, our rehabilitation clothes, our clothes that we would wear on the job, or even what we'd wear at home. So we may be in a position where stools at home in our garages, we don't need them because they stiffen and they support when needed. It sounds really outlandish, but these two examples that you see here, so the 3D knit biosuit and also the 3DO non-Newtonian forms, these are products that are presently there and are being heavily discussed about this. And I can tell you from behind the curtain of when I've been discussing with ASTM, this has been one of them topics of what about the semi-rigid structures? What about this for the future? It's incredibly exciting. I'm trying to hold in my enthusiasm, if I'm honest. But this really rolls itself back, though, to the idea of that testing. Make sure that we do it right. It's all right having these newer technologies, and it's all right to have the idea of being able to stiffen in particular behavior, but how reliable can we say it would be? Can we be sure we're doing it right? And this is what relates right back again to the discussions on the standards committees and just thinking about how we safely do this moving forward. And I know some of you will have been thinking, you've not discussed a single thing about control. Control is extremely interesting. I've heard a lot of people say to me, well, do we just do electromyography? Anybody who doesn't know electromyography, your muscles contract under a direct signal sent from the brain to literally cause contraction process. We can read this process by using differential amplification, which will allow us literally just to measure one value and another, and then we can measure that value as it comes through, if you will. This is a technology that's been around for a long time, and a lot of people have played with this method as much as possible. Now, for doing something dead straightforward, like controlling, say, a prosthetic arm to create an open and close function on a hand, we can do that very reliably. We can do that pretty well, to be honest. However, when we start to consider the human body moving, this is a whole new ball game. Think of it like this. When I go to stand up, I will trigger my abdomen. As I trigger my abdomen, it'll allow me to support my quadriceps, which will fire my quadriceps, allowing me to also move at the same time. However, if I'm just going to use the signal from my abdomen to control a motor for something that's an active exoskeleton, what happens when I sneeze? As I sneeze, I fire my abdomen. So what I end up doing is the world's most hilarious sneeze. It's chew. And so the whole body moves forwards. So this is why at the moment, this is a noisy approach. And what we're looking to try and do is move this a little bit more forwards. So there's two examples here that I really wanted to discuss that a little bit further. The one to the left is a very famous example known as the Myo band. Myo being Greek for arm electricity. I'm trying to think of the actual term. And to the right, these are embedded, invasive EMG signals. The problem that we have is trying to categorize what we do. Now, a colleague on my team, and I know teams all over the world, are looking at trying to use electromyography sensors around the body and trying to categorize what someone is attempting to do. So, for example, you may be walking up the stairs, you may be sneezing, you may need nip to the loo, ensuring that there's not any uncomfortable misfires. So what we're attempting to do is categorize each motion, each action in which we do, then pass this through to a neural network or AI, as some of you may know it. What we then want it to be able to do is to adapt with each and every individual system. This is not a copy and paste. It would need to be individual to every single person. This system then allows for, you can categorize what someone does. And in essence, you would end up with an exoskeleton or a prosthesis, because this system works in the same place. You'd end up with an exoskeleton or a prosthesis, which will learn with you. It would develop with you. It would become your, new mobile phone. It would be the thing that you would wear, and it would actually learn and actually develop with you as an individual. This is what rolls it back again to the disposal aspect. What if we have a skeleton and we need to get rid of it? If we're using to this level of data, we need to be very careful of how we progress forwards. So, for example, if we are going to make this so that the system could connect to our internet to do a backup, for example, we need to be sure that we can protect it. So we need to think about hacking. Again, this is a topic that's been quite heavily talked about, and a colleague, again, on the F48 is really discussing this and ironing this topic down that little bit further. It's a very, very exciting future. But again, these are the questions and these are the topics that we're already discussing now, even before the technology is fully commercialized, because it's vital that when we do it safely. So this is a little bit of a nerve-wracking moment for me. I wanted to really iron down a little bit further to Sean's comments about how me and him got connected and the advancements and the gratefulness from my perspective to Tinius Olsen and also the ASTM family actually are, and how and where we are at the moment. Now, if you joined us at our last one, you'll know that I talked about the very first skeleton that we started to look at. I'm happy and excited to unveil our new skeleton that we call Liberty. Because of the collaboration that we've been working with Sean and all the guys at Tinius Olsen, we have been able to develop a new type of 3D printed technology, which I say 3D printed technology, I should say we're using a sandwich material where we've actually produced a hyperelastic and semi-rigid material. So this is a sandwich material where the outside is hyperelastic for conformability around the body. So it just fits and is more comfortable to wear. From the assistance that we've had, I've given you a bit of an FEA render just to give you an idea of the type of testing and how we were actually producing this, just looking at dog bones and producing a lot of, as you can imagine, lots of breaking. And to the bottom of this is some of our very first running trials that we've done, where we've actually examined the exoskeleton in physical motion. Christina, who is the young woman that's actually forwarded the original idea behind this, simply asked this: why is there not something out there that children can wear that can help them live a normal life who are ill? And you know, originally when I saw this, I kind of thought, what's she talking about? There must be millions of these in the world. She was right. There was nothing. Recently, there has been one development. Her hope as a youngster, she always wanted to come up with something that everybody could have, that was accessible to everybody. So we jumped on the endeavor, and it's been a rabbit hole of just pure excitement. So what we've done is we've developed, tested, and we are at our very first prototype. Again, we call it Liberty because we hope that whichever child ever gets to wear this will feel liberated in living a normal and happy and productive, and let's face it, fun life for the future. The technology itself is 3D printed. It is a combination of a TPU with an internal core of a nanocomposite copper with PLA. And the performance of this, well, you'll see at the bottom, that's me wearing it. So where I thought, you know what, before putting this on any pediatrics, let's put it on somebody who's daft enough to wear it. So I wore it because I'm that confident in what we've done. And again, this is all from the support and the real encouragement from Sean, from Tinius Olsen, and also everybody on the ASTM panel. So finally, let me summarize. To the right, you'll see what we call Marsha. So the white skeleton, we called it Marsha after Christina because her last name is Marshall. And we quite liked that. That just sounded quite nice with it. And we learned an awful lot from that. To the right is our Liberty skeleton to give you an idea of the size of what you were looking at. And we're very excited about this. And we're hoping to see a lot, even massive more advancements. The one thing I didn't say about the new Liberty skeleton is we've taken a combination of both exosuit and exoskeleton. We are mimicking muscular contraction and also offering a passive support structure. And we think we've got something very special to give to the world. So let me summarize. Moving forwards for exoskeletons, we will see structures that are more affordable. We will see exoskeletons appearing not just for the big manufacturing floors. We will start to see them appearing for fun. We'll start to see them appearing for sports, for people who used to be runners, for example, who want to be able to run once again. We will see this. We will see materials which will stiffen under certain conditions, and we'll see some real changes in the world. And it's super exciting from my perspective. And if you are interested in learning more about what we've discussed here and what's going on, I put you a few slides onto here. One is from our Center of Excellence head, Bill Belay, and from our site manager, Nora. This is called the Excellent Exo Chat. If you are interested about what's going on, this is a podcast I've got to recommend. It's fantastic. One of our members from the exec team on the F-48 writes the Exoskeleton Report, where he gathers all the data about present developments and what's really going on in the world. It's great to do. And the link here will take you directly to F-48 Exoskeleton and Exosuits. If you do want to get involved, do reach out, and that will go straight to Bill and Nora. And finally, I run a project with schools to encourage schools to understand about, because the problem is if you go into schools about exoskeletons, all kids instantly think that you're making Iron Man, which is nice, but not very true. What this is this project is called Engineering Humans. I've been able to bring together some of the best and brightest engineers. I can't just say engineers, I should say people from STEM who work on exoskeletons from around the world. I've interviewed them, got their backgrounds, and also I've produced an exoskeleton for schools where kids can print their very own working exoskeleton. And all of this is for free. So if you are interested, contact me, contact Sean, and I will gladly give you all the materials and offer you some support where needed. Other than that, let me just say a massive thank you for listening. And my name's Matt Dickinson.
Fantastic. Well, I can see why you're so excited, Matthew. It's an awful lot to take in there. It's amazing. I can see, I think we've got a question for you down here. Anybody else before you go, please do ask questions. I think you've been blown away from what you've heard today. So please do type in the Q&A box and take advantage of Matthew and Sean being here while they are. I've got a question here from Nikki. It says, what is the working temperature range of the Newtonian foam?
For the D3O, it's still very experimental. Now, the full temperature range, I would be completely deceitful if I'd said that I know exactly what that is. From what I understand from the guys who manufactured it, this is purely designed around atmospheric temperatures. It is not something that could withstand huge, large and lower temperatures. If you are interested, do reach out to them. They're incredibly helpful. Their products are fascinating things.
Hope that answers your question as best, Nikki. Otherwise, do come back to us. Fabulous. Anybody else have a question while we still have the guys here? Oh, go. One from Deb. Will a copy of the slides and presentation be available after this? A few of my colleagues were unable to dial in just now. Deb, the answer to that short answer is yes. I will be, once it's all been downloaded and put into place, I will send out a link to everybody who can re-watch this. And of course, you're very, very welcome to forward it on to anybody who is interested and could find value in it. Absolutely. Wonderful, thank you. Anybody else? Here we go. I've got one here. Where can I get the price of passive exoskeleton? Is that a simple question? It doesn't sound like a simple question.
Yes.
Matthew, let me jump in here on this one. So, and to the person who asked the question about the price, let me put it to you in a term that technology has opened our eyes to. When the exoskeleton or exosuits were produced in the 1980s all the way into the mid 2000s, like 2010, 2015, a common price was a little on the other side of a couple £100,000. And that's a lot of money. the target now with the additive material and the printable material is that we could get a exosuit into the public realm for less than 10,000 pounds. And hopefully that would be covered under some type of insurance and or programs that are available to those that are disadvantaged and that are mobile restricted. But that is approachable. And that is the look at the price as current. And as technology increases with AI, that will drive the price down even further.
Amazing. Fabulous, thank you. I hope that answers the question as best it can. Nicholas here has one. Can you elaborate on the sandwich material for Liberty and why copper or PLA?
Right. This is, I'm going to, Sean, you may need to stop me.
I will.
So the hyperelastic material being TPU in itself only fails under roughly 4 times its own original for its own original positional aspect. What we were interested in is if you're going to wear something which is 3D printed, the possibility of shearing, failure around it, and sharp elements and splinters. Because my biggest concern is this is aimed for pediatrics and it's aimed for children, and actually any skin, if you will. Now, what I wanted to do is if a failure was going to happen, I wanted to be able to design components that when they failed, they would simply go limp. So if you will, the stiffened aspect, and when it failed, you could actually feel how poor it was performing. So by using, in fact, by using the relationship with TR, I was able to test different aspects. Now I can see what you're probably thinking, surely there's much better materials out there. Now I thought this when it came to nylon. So nylon's a great one. However, a little bit on the pricey side, as everybody in the audience will be well aware. But when it came to the use of PLA, what we really started to notice was that the TPU, when it lays down, it lays down around 245 degrees. PLA is around 180 to 190 roughly. When it became to contact with that TPU, it actually didn't affect the TPU's ability to hyperelastically deform as we wanted it to, in essence, making a sandwich. It wasn't a composite. However, when we looked at doing the same type of production with a nylon, with the temperatures, melting temperatures being so close, when they become into touch with each other, you'd end up with a composite structure on the surface, which really compromised what we wanted to achieve. It was dead easy to, if you will, deform it and actually break it. Now we've been developing a little bit more behind this, and that's just a real summary of where we got up to with this. Yes.
Yeah, so let me just encompass this a little bit, and you're right. This is, to answer Nicholas's question in a more broad spectrum, is that this is the relationship between universities, testing organizations, and ASTM. And when you're collaborative with these international organizations, what we're doing at UCLan and what we're doing across the world in multinational is we're trying all different materials at simultaneous times, and then we collectively get together to find the good and the bad, the pros and the cons, and it's a very dynamic situation. So to answer why this is, 6 months from now, we may have a different answer for you. but right now, this is what we're utilizing currently, and it's a very dynamic situation. And that's about the best we can answer that without having this go on another hour. And Johanna, I see we have another question. The easiest way to reach out, I think if that person wants to reach out to either Matthew or myself, we can put up our contact information, which I'm free to share, of course.
Fantastic. And if you're happy with that, I can always add it to the email I send out.
That would be wonderful. No problems on my side.
Yeah, thank you. Yeah.
Super. There you go, Ben. Wonderful. Are there any other questions? I see there's something in the chat there. Is that a question or is that someone saying something? Oh, that's fine. That's Nikki confirming her answer. Wonderful. Okay. Any last questions before I let these guys go? think we're there. So obviously in the email roundup that I do, you'll have these guys' contact details. So if you do have any questions that come to you, if you're anything like me, I have the best question ever about half an hour too late. If you're like me, then don't worry, it's never too late to ask that important question. So it just leaves me to say, Sean, Matthew, thank you so much. That was absolutely fascinating. I can't believe all the things you can do and what your plans are. They sound incredibly exciting. So I understand why you're as excited as you are about the collaboration. It's fantastic. And thank you very much for all those who have watched live with us, and hopefully all those who are watching this on a recording. Thank you very much for your time, and have a lovely rest of your day.
Thank you.
Thank you, Jonna.
Thank you.
Thank you, Matt. I'll chat with you soon.
Yeah, see you soon.
All right. Yep.